Hello, everyone. Welcome to another episode of ML for Noobs. Now, we're finally ready to get started. So, last video we did the setup for Jupyter Notebooks, and this video we're finally getting started. So, let's go ahead and take a look at what this looks like. The format is something I'm still experimenting with, but we're going to see how this works. All right, so what I'm going to do is I'm going to play the video and I'm going to speed it up a little bit because this guy talks real slow. So I'm going to play a video and then stop it at various places where I find that I do not follow, or if I want to try something out, or if I'm just thinking about something. I'll think about it out loud and discuss it with you without you speaking. And then once we actually get what's going on, we'll proceed. So without further ado, I really do hope that this audio quality is all right, because that's my biggest concern. I'm not really sure how I could possibly play a video and just have that work, but we'll see. We'll give this a shot, see if it works. If it doesn't, then what we're gonna do is we're probably gonna see if there's another way to get this done. But if it's not an issue, we're just gonna go with it anyway, right? So let's switch to full screen mode. Looks like we're all set. Let's go.
Because there's a lesson zero. Lesson zero is why do you need a GPU and how do you get it set up? So if you haven't got a GPU running yet, then go back and do that, so you can access a Jupyter Notebook and then you're ready to start the real stuff. So if you're ready, you will be able to see something like this. And in particular, hopefully you'll go to notebook tutorials that pops up 00 here. As this grows using Word files, notebook tutorial top, and you will have used your Jupyter Notebook to add one together. And you can result.
Alright, see if we got that set up. So coming back to Crussell again, last time we did all this, it's already set up. So at this point we just need to run up the notebook and go to the same thing that he's showing us, which is notebook tutorial under, what is it, course v3 NBS DLL1 whatever. Alright, so let's try and open that up. Course v3 NBS DL1. Alright, that's notebook tutorial. And at this point we should be seeing the same thing that he is seeing. Alright, looks good. Let's proceed.
And hopefully you find these four keyboard shortcuts. So the basic idea is that your Jupyter Notebook has rows in it. You can have pictures in it. You can have charts in it. And most importantly, you can have code in it. So the code is in Python. How many people have used Python before? So yeah, well, that's great. If you haven't used Python, that's probably okay, right? It's a pretty easy language to use. But if you haven't used Python, this will be motivating because they're going to see the get to this. So, as I said, there are things like this where people in the room, this is one of those bits you can't do in the book, but it's not time like this in the lesson because you got some excellent. Okay. Right, so yeah, this will learn more about your life. We can go back on this and make sure that you can keep this running using the information in policy 3 or something.
Yeah, the volume is not really high enough, so I'm going to try to slow it down.
Really interesting device for a data scientist because it kind of lets you run interactive experiments, and it lets us give you not just a static piece of information, but it lets us give you something that you can actually interactively experiment with. So let me explain how we think works well to use these notebooks and use this material. This is based on the kind of last 3 years of experience we've had with the students who've gone through this course. First of all, it works pretty well just to watch a lesson end to end. Right? Don't try and follow along because it's not really designed to go to speed where you can follow along. It's designed to be something where you just take in the information, you get a general sense of all of the pieces, how it all fits together. Okay? And then you can go back and go through it more slowly, pausing in the video and trying things out, making sure that you can do the things that I'm doing, and that you can try and extend and do it from your own. Okay? So don't worry if things are zipping along faster than you can do them. That's normal. Also, don't try and stop and understand everything the first time. If you do understand everything the first time, good deal. But most people don't, particularly as the lessons go on, they get faster and they get more So at this point, we've got our notebooks going, we're ready to start doing deep learning, and so the main thing, hopefully you're going to agree at the end of this, is that you can do deep learning, regardless of who you are.
Yay!
You do at a very high level, a world-class practitioner level deep learning. Okay. So your main place to be looking for things is course d3.fast.ai, where you can find out how to get a GPU, other information, and you can also access our forums. You can also access our forums, and on our forums you'll find things like how do you build a deep learning box yourself, and that's something that you can do later on once you've kind of got it. Who am I? So why should you listen to me? Well, maybe you shouldn't, but I'll try to justify why you should listen to me. I've been doing stuff in machine learning for 25 years. I started out in management consulting, where actually initially I was, I think, McKinsey and Company's first analytical specialist. I moved to general consulting. I ran a number of startups for a long time. Actually became the president of Apple, but actually the thing I probably was proud of in my life is I got to be the number one ranking contestant in Apple competitions globally. So I think that's a good practical, like can you actually train a predictive model that predicts things? Pretty important aspect of data science. I did found a company called Clinic, which is the first medical deep learning company. Nowadays I'm at the University of San Francisco, and also co-founder of Mitchell of FastAI. So I've used machine learning throughout that time. I guess I'm not really
Wow, this guy's a badass.
I'm not really an academic type. I'm much more interested
Rank number
in
one.
to do useful things. Specifically through FastAI, we are trying to help people use deep learning to do useful things through creating software to make deep learning easier to use at a very high level, through education, such as technology now, through research, which is where we spend a very large amount of our time just researching to figure out how can we make deep learning easier to use at a very high level, which is something as we're seeing in software and education, and by helping build a community, spanning through the forums, so that practitioners can find each other and work together. So that's what we do. So this lesson, Ethical Deep Learning Coders, is kind of the starting point in this journey. It contains 7 lessons, each one's about 2 hours long. We're then expecting you to do about 8 to 10 hours of homework.
Wait, what?
So we'll end up doing something around 6 or 8 hours.
Get the hell out. So you're saying after 7 lessons, I can create a world-class model to identify movie review sentiment? Whoa. Netflix recommended movies? Alright, it says Netflix there, but doesn't necessarily mean that you can compete with Netflix. But that's pretty awesome. I mean, these are very, very specific outcomes.
I will say there is a lot as to how much people play to this. I know a lot of people who work full-time on FastAI. Some folks who do the 2 parts and spend the whole year doing it really intensively. I know some folks watch the videos, sometimes they even do it homework, and at the end of it, general sense of what's there. So there's lots of good ways to do this. But if you follow along with this kind of 10 hours a week or so, approaching 7 weeks, by the end, you will be able to build a classification model on pictures that you choose that will work at a world-class level. You'll be able to classify text, again, using whatever text you're interested in. You'll be able to make predictions of kind of commercial applications like sales. You'll be able to build recommendation systems such as the one used by Netflix. Not toy examples, many of these, but actually things that can come from Apple competitions, that can be everything that's in the academic community, very, very high level versions of these things. So that might surprise you that something of the prerequisite here is literally 1 year of coding and high school math, but we have thousands of students now who've done this and shown it to you. You will probably hear a lot of naysayers, less now, a couple of years ago when we started, a lot of naysayers telling you you can't do it, or you shouldn't be doing it, or that deep learning has got all these problems. It's not perfect. These are all things that people claim about deep learning, which are either pointless or untrue. It's not a black box, as you'll see. It's really great for interpreting what's going on. It does not need much data for most practical applications. You certainly don't need a PhD, graduate master mark, so it doesn't stop you from doing deep learning in PhD. I certainly don't. I have a philosophy degree and nothing else. It can be used very widely in lots of different applications, not just for vision, which is very well done. You don't need lots of hardware. That's a 36 cent an hour server. It's more than enough to get world-class results in most problems. It's true that maybe this is not going to help you build a sentient brain, but that's not our focus. Okay, so for people who say deep learning is not interesting, this is not really AI, not really a conversation I'm interested in, we focus on solving interesting real-world problems. What we're going to be able to do by the end of lesson 1, this was an example of Mitchell, who's actually in the audience now, so it's in most of his course as well. This is an example of something he did, because he downloaded 30 images of people playing cricket and people playing baseball, and ran the coaches who they
What?
nearly perfect test plan.
30 training images.
So this kind of stuff you can build with some fun hobby examples like this, or you can try stuff as we'll see.
I can't wait to see this.
So this is down here for about 50 by the end of this one. We're going to start by looking at code, which is very different to many of the academic courses. So those of you who have a kind of engineering or math or a science background, this is very different to the approach where you start with lots and lots of theory, and then eventually you get to a postgraduate degree and finally you're acquainted with something useful. We don't want to build useful things today. Now that means at the end of the day, you won't know all the theory. Okay? There will be lots of aspects of what we do that you don't know why or how it works. That's okay. You will learn why and how it works over the next 7 weeks. But for now, we found that what works really well is to actually get your hands dirty coding, not focusing on theory. Because there's still a lot of artisanship in deep learning, unfortunately. It's still a situation where people who are good practitioners have a really good feel for how to work with code, how to work with data. You can only get that through experience. And so the best way to get that feel for how to get good models is to create lots of models. To and study them carefully. And Jupyter Notebook provides a really great way to study them. So let's try that. Let's try getting started. And so to get started, you will open your Jupyter Notebook, and you'll click on this one. That's one, hits. And it will pop open, look something like this. So
Lesson 1. Alright, hang on. Lesson 1 pets. There we go. Let's click on that. Apparently what you want to do with each one is you want to make sure you're making a copy of the file. So I'll go ahead and do that. Make a copy, just so I don't screw up the original file. Yeah, leave page. Wait, hang on. Where'd that go? Alright, let me open that up. Well, come on then. Alright, there we go. So that's Pat's copy 1. Alright, what do we got?
Run cell in the Jupyter Notebook by clicking on it and pressing run. But if you do so before, you will know that you're not building learning practitioner, because building learning practitioners have keyboard shortcuts. And the keyboard shortcut is Shift Enter. Given how often you have to run the cell, don't be going all the way up here finding everything there, just Shift Enter. Okay, so it's like that, Shift Enter, Shift Enter. Up and down, move around, pick something, run, Shift Enter, Shift Enter. Okay. So we're going to go through this quickly, and then later on we're going to go back over it more carefully. So here's a quick version of this. So here we are in lesson 1, and these 3 lines is what we start every notebook with. These things starting with the set are special directives to Jupyter Notebook itself. They're not like they're called packages. And these 3 directives, details aren't very important. Basically, it says, hey, if somebody changes the underlying library code while I'm running this, please reload it automatically. If somebody asks to plot something, then please plot it here. So just put those 3 lines above it. The next 2 lines load up the FastAI library. What is the FastAI library? So it's a little bit confusing. FastAI is the name of our software, and then Fast.ai is the name of our organization. So if you go to docs.fast.ai, this is the FastAI library. Okay, we'll learn more about it in a moment, but now to realize everything we're going to do is going to be using basically either FastAI or the thing FastAI sits on top of, which is PyTorch. PyTorch is one of the most popular libraries for deep learning in the world. It's a bit newer than TensorFlow, so in a lot of ways it's more modern than TensorFlow. It's extremely fast growing, extremely popular. We use it because we used to use TensorFlow a couple of years ago, and we found we could just do a lot more quickly with PyTorch. And then we have this software that sits on top of PyTorch and lets you do far more things, far more easily than you can with PyTorch 1. So through combination, we'll be talking more about it. But now, just know that you can use FastAI by doing 2 things. Importing star from FastAI, and then importing star from FastAI got something, where something is the application you want. Apparently FastAI has 4 applications: computer vision, natural language text, tabular data, and library filtering. And we're going to see lots of examples of all of those during the segment. So we're going to be doing some computer vision.
Alright.
At this point, if you are a Python software engineer, you are probably feeling sick because you see me go import star. Which is something that you've all been told you never ever do. Okay. And there's very good reasons to not use import star in standard production code with most libraries. But you might also think those of you that do something like MATLAB, it's kind of the opposite. Everything's there for you all the time. You don't even have to import things all the time. It's kind of funny, you've got these 2 extremes of like how do I code. You've got the scientific programming community that has one way, and then you've got the software engineering community that has another. Both have really good reasons for doing things, and with the FastAI library, they actually support both approaches. In a Jupyter Notebook, where you want to be able to quickly, interactively try stuff out, you don't want to be constantly going back up to the top and importing more stuff and trying to figure out where things are. You want to be able to use lots of tab complete, be very experimental, so import start is great. Then when you're building stuff in production, you can do the normal template style, software engineering practices. So don't worry when you see doing stuff.
Alright, just get to the point. This is taking forever, man.
It's not that there are no rules in data science programming. The rules are different. Right? When you're training models, the most important thing is to be able to interactively experiment quickly. Okay, so you'll see we have to use a lot of very different processes, styles, and stuff to what we're used to. They're there for a reason, and we'll learn about them. In a design a very interesting modular way, we'll things and use them quickly without any problems. Okay, so we're going to look at some data. And there's 2 main places that we can get data from doing this. One is from academic data sets. Academic data sets are really important, really interesting. They're things where academics spend a lot of time curating and gathering a data set to show how well different kinds of approaches work with that data. There's kind of design data sets that are challenging in some way, require some kind of breakthrough that you work. So we're going to start with an academic data set called PET data set. The other kind of data set we'll be using during the course is data sets from the Kaggle competitions platform. Both academic data sets and Kaggle data sets are interesting for us, particularly because they require performance-based science. That's to say, you want to know if you're doing a good job. So with Kaggle data sets that come from competition, you can actually submit your results to Kaggle and see how well you've gone in that competition. And if you get in about top 10%, that's how you're doing pretty well. For academic data sets, academics write down in papers what the state of the art is. So how well did they go with these models in that data set? Okay. So this is what we're going to do. We're going to try and create models that get run up towards the top of Kaggle competitions, but we actually
Alright, yeah.
or that meet or exceed academic state of the art competition results. So when you use an academic data set, it's important to cite it. So that's what you ask us to distinguish between 37 different categories of dog breed and cat breed. So that's really hard. In fact, in every course until this one, we've used a different data set, which is one where you just have to decide something a dog or is it a cat. So it kind of gives you a chance right away. And dogs and cats look very different, whereas lots of dog breeds and cat breeds look pretty much the same. So why have we changed our data set? We've got to the point now where deep learning is so fast and so easy that the dogs versus cats problem, which a few years ago was extremely difficult, at 8% accuracy, was is now too easy. Our models were basically getting everything right all the time without retreating, and so they weren't really a lot of opportunities for me to show you how to do all sorts of different stuff. So we picked a harder problem this year. So it's the first class where we're going to be learning how to do this difficult problem. And this kind of thing, where you have to distinguish between similar categories, is called, in academic context, it's called fine-grained classification. We're going to do the fine-grained classification task of figuring out how to keep that. So the first thing we have to do is download and extract data.
Alright, so right now it's downloading this, the data set. And it's decompressing it. So that's what it's doing. You can run this and see what the contents of that directory are. Alright, so we see images and annotations. Set those to variables, path ano and path image. Okay.
These bits types, okay, because type programming language we're used to seeing them, but type programs are less useful. But if you think about it, you don't actually know how to use a function unless you know what type each thing is you're providing it. So we make sure that we give you that type information directly here in the home. So in this case, URL is a string, and the file name is either a path or a string, and it defaults to nothing. And the destination is either a path or a string, it defaults to nothing. So we'll have more shortly about how to get more documentation about the details of this. But for now, we can see we don't have a passing file name or a destination, it'll figure it out for us from URL. So, and for all of this, this will be using the course. We already have constants defined for all of them, right? So this URLs module of class actually. So that looks like okay. So download that to some create a path and unpair for us, and we'll then return the value of path. Okay. And then in Jupyter Notebook, it's kind of handy. You can just write a variable on its own. Right? And semicolon is just an end statement under a path. So it's like doing this. You can write on its own and it ends it. You can also say print, right? But again, we're trying to do everything fast and correctly. Just write it, and here is path. Where it's giving us that data. Next time you run this, since you've already downloaded it, you won't download it again. Since you've already unpacked it, you won't unpack it again. Everything's kind of designed to be pretty automatic, pretty easy. There are some things in Python that are less convenient to interact with use than they should be. For example, we do have a path object. Seeing what's in it actually takes a lot more typing than I would like. So sometimes we add functionality into existing Python stuff. One of the things we do is we add ls method to paths. So if you do path.ls, here is what's inside this path. So that's what we download. So when you try this yourself, you can wait a couple of minutes for it to download, unzip, and then you can see what's in it. If you're an experienced Python programmer, you may not be familiar with this approach of using slash like this. This is a really convenient function. It's part of Python 3. This functionality comes up with path lib. These are path objects. Path objects are much better to use than strings. It lets you basically create subpaths like this. It doesn't matter if you're on Windows, Linux, Mac, it's always going to work exactly the same way. So here's path to the images in that dataset. Alright, so if you're starting with a brand new dataset, trying to just keep running on it, what do you do? Well, the first thing you're going to do is probably see what's in there. So we found that these are directories in there. So once it is images, there's a lot of functions in Fast for you. There's one called get image files that will just grab an array of all the image files as an extension in the path. And so here you can see we've got lots of different files.
Get image files. So let's see what that looks like when I give it a shot. So we go here, shift enter to run, and okay, so we're just selecting 5 of them, and I assume the :5 syntax means the last 5. I'm not sure. But anyway, so we're getting a list of 5, and that seems fine. If I remove that, well, let's just say f names. What's that gonna look like? Whoa, okay, that's a long list. So yeah, it does make sense. Siamese 87 is how it starts, so if I run this, yeah, it gets the first 5 then, not the last. Alright, anyway, let's keep going.
So the interesting bit then is how we get the labels. So in machine learning, the labels refer to the thing we're trying to predict. And if we just eyeball this, we can immediately see that the labels are actually part of the file name. See that? Right? So
right.
Path / label _ number extension. So we need to somehow get a list of these bits of each file name, and that will give us our labels. Because that's what we need to go deep learning model. It needs pictures, so files containing images, and it needs labels. So in FastAI, this is made really easy. There's a object called image data bunch. The image data bunch represents all the data we need to build a model. And there's basically some factory methods which try to make it really easy for you to create that data bunch. We'll talk more about this shortly. The training set, validation set, with images and labels for you. Now in this case, we can see we need to extract the labels from the names. Okay, so we're going to use from name RE. So for those of you who's Python, you know RE is the module in Python that does regular expressions. This is really useful for extracting text. I just went ahead and created the regular expression and extract the label from this case. Okay. So
Alright, so that seems pretty straightforward. Create a pattern. I don't know what this NP random seed thing is. I guess you're generating random seed.
This is the vector expression pattern that's going to be used to extract the label from the file name. We'll talk about transforms later. And then you also need to say what size images do you want to work with. So that might seem weird. Why do I need to say what size images I want to work with? Because images have size. You can see what size images are. And honestly, this is a shortcoming of current deep learning technology, which is that the GPU
Name
has to
error
provide
BS is not defined.
things at the same time in order to be fast. And so if images are different shapes and sizes, you can't do that.
I didn't run
So we
that.
actually have to make all the images the same shape and size. In part one, of course, we're always going to be making images square shapes. In part two, we'll learn how to use rectangles as well. It turns out to be surprisingly useful. But pretty much everybody in pretty much all computer vision modeling, nearly all of it, uses this approach of the square. And 224 by 224, the reason to learn about is extremely common size that most models tend to use. So if you just use size 224, you're probably going to get pretty good results most of the time. And this is kind of the little bits of arts and shit that I want to teach you folks, which is like what generally just works. Okay, so if you just use size 224, that'll generally just work for most things most of the time. So this is going to return a data match object. And in FastAI, everything you model with is a data match object. We're going to learn all about what's in them and how to look at them and so forth. But basically, a data match object contains 2 or 3 data sets. It contains your training data, we'll learn that shortly, it contains your validation data, and optionally it contains your test data. And for each of those, it contains your images and your labels, or your text and your labels, or your tabular data and your labels and so forth. And that also is there in this one place. Something we'll learn more about a little bit is normalization. Generally, in really long machine learning tasks, you have to make all of your data about the same size, specifically about the same mean and about the same standard deviation. So there's a normalize function that we can use to normalize our data mesh that way.
Okay.
Okay, Rachel.
Now that looks a little bit different from what I'm looking at over here. Okay, so it just says dot normalize, so I don't suppose that's a huge difference. Now let's go ahead and show the data. So I got all this, path image, f names, so these are the names that it's going to iterate through, and then the pattern, and DS transforms, I have no idea what that is, and get transforms, and then size is 224, that's 224 by 224 pixels, BS is 64, I think we set that up here. Click kernel restart. Batch size, that's what it is. Alright, and then normalize ImageNet stats. Okay, sounds good. So this is all pretty straightforward. I don't know what this DSTFMS is, but I guess that's something we're going to get to at some point. I can see, okay, it's showing a bunch of stuff, and rows equal 3 means it's showing 3 rows, 7, 6 fig size, whatever that is. And okay, so it's just showing some images, basically saying that, okay, it's recognized them, I presume.
So this is what I'm going to learn about shortly. Basically, this thing called transforms is used to do a number of things. One of the things it does is to make something size 224. Let's take a look at a few pictures. Here are a few pictures of things from my data mesh. So you can see data.showBatch can be used to show me the contents of some of the contents of my data mesh. So it's 3 by 3. And you can see roughly what's happened is they all seem to have been kind of zoomed and cropped in a reasonably nice way. So basically, what it will do is something called by default center cropping, which means we'll grab the middle bit and it will also resize it. So we'll talk more about the detail of this. This turns out to actually be quite important. But basically, a combination of cropping and resizing is used. Something else we'll learn about is we also use this to do some quotate augmentation. So there's actually some randomization, how much and where it crops and stuff like that. And that's the best part here is some cropping and some resizing. Often we also do some padding. So there's also all kinds of different ways that depends on data augmentation, which we're going to learn about shortly.
Okay.
And what does it mean to normalize images?
So normalizing images we're going to learn more about later in the course. But in short, it means that the pixel values, we're going to learn more about pixel values. Pixel values start out from 255, and some pixel values might tend to be really, some channels, there's red, green, and blue. So some channels might tend to be really bright, some might tend to be really not bright at all, some might vary a lot, some might not very much at all. It really helps train a deep learning model. If each one of those red, green, blue channels has maybe 0.
So so far we've not actually done anything. This is just pre-processing and setting things up for the learning bit.
Much more about details, but if the data is not normalized, it can be quite difficult for your model to train well. So if you do have trouble training the model, but you can check this to be normalized.
As GPU then will be power to as a size to be 6 more practical instead of utilization.
So we're going to be getting into that shortly, but the brief answer is that models are designed so that the final layer is size 7 by 7. So we actually want something where if you go 7 times 2 100 times, you end up with something sort of size. Yeah, all these details we are going to get to. And the key things are to get you training the model as quickly as possible. But one of the most important things to be a really good practitioner is to be able to look at your data. Okay, so it's really important to remember you go to data.show match and check. Well, surprisingly how often you actually look at the data set you've been given and you realize it's got weird black borders on it, or some of the things are text covering up some of it, or some of it's rotated in odd ways. So make sure you check. Okay. And then the other thing you're going to do is not just look at pictures, but also look at the labels. And so all of the possible label names are quotable classes. So the data bunch you can print out for data.classes. And so here they are. That's all of the possible labels that we found by using that vector expression on files. And we learned earlier on in that Prosa at the top that there are 37 possible categories. And
We got 37.
A data bunch will always have a property called C, and a property called C, the technical details we're going to get to later, but for now you can kind of think of it as being a number of classes. For things like regression problems and label classification and stuff, that's not exactly accurate, but it'll do for now. It's important to know that data.c is a really important piece of information that is something like, or at least the classification problem is the number of classes.
Okay.
But believe it or not, we're now ready to train a model. And so a model is trained in FastAI using something called a learner. And just like a data bunch is a general FastAI concept for your data, and from there are some subclasses for particular applications, like image data bunch. A learner is a general concept for things that can learn to fit the model, and from that there are various subclasses to make things easier. In particular, there's one called home learner, which is something that will create a convolutional neural network for you. We'll be learning a lot about that in the next few lessons. But for now, just note that to create a learner for a convolutional neural network, you just have to know two things. The first is, what's your data? And not surprisingly, it takes a data bunch. And the second thing you need to tell is, what's your model? Or what's your architecture? So as we learned, there are lots of different ways of constructing a convolutional neural network. But for now, the most important thing for you to know is there's a particular type of model called the ResNet, which works extremely well nearly all the time. And so for a while at least, you really only need to be choosing between two things, which is what size ResNet you want. How big is it? We'll learn all about details in a minute. There's one called ResNet 34, and there's one called ResNet 50. And so when we get started with something, I'll pick a small one. Okay,
So I'll just assume that ResNet is some sort of magical black box for now. I imagine at some point he's going to dig into that a little bit more, but okay, ResNet.
So that's kind of it. As much as you need to know to be a pretty good practitioner about architectures for now, which is that there's two architectures, two variants of an architecture that work well, ResNet 34 and ResNet 50. Start with a small one, you see the one. So that's all the information we need to create a convolutional neural network learner. There's one other thing I'm going to give it though, which is a list of metrics. Metrics are literally just things that get printed out as a string. So I'm saying I'd like to print out the error rate. Let's see. See, the first time I ran this on a newly installed box, downloaded something. What's it downloading? It's downloading the ResNet 34 pre-trained weights. Now what this means is this particular model has actually already been trained for a particular task. And that particular task is that it's trained on looking at about 1.5 million pictures of all kinds of different things, 1,000 different categories of things, using a data set called ImageNet. And so we can download those pre-trained weights. So we don't start with a model that knows nothing about anything, but we actually start with a model that knows how to recognize the 1,000 categories of things in ImageNet. Now I'm not sure, I don't think all of these 37 categories of pet were in ImageNet, but there were certainly some kinds of dog, there were certainly some kinds of cat. So this pre-trained model already knows quite a little bit about what pets look like, and it certainly knows quite a lot about what animals look like and what photos look like. So the idea is we don't start with a model that knows nothing at all, but we start by downloading a model that knows something about recognizing images already. So it downloads for us automatically the first time we use it, the pre-trained model. And then from now on, it won't be downloaded again, it will just use the one we've got. This is really important. But when we find out, this is kind of the focus of the whole course, which is how to do what's called transfer learning. Take a model that already knows how to do something pretty well, and then so that it can do your thing really well. Okay, pre-trained model, and then we fit it so that instead of picking the 1,000 categories of ImageNet data, it picks the 37 categories of pets using your pet data. And it turns out by doing this, you can train models in 1/100th or less of the time of regular model training with 1/100th or less of the data of regular model training. In fact, potentially many thousands of times less. Remember I showed you the slide of Nigel's lesson 1 project from last year? He used 30 images. And there's not cricket and baseball images in ImageNet, right? But it just turns out that ImageNet's already so good at recognizing things in the world, because 30 examples of people playing baseball and cricket was enough to build a nearly perfect classifier. Okay. Now, you would naturally be potentially saying, well, wait a minute, how do you know that it was going to actually recognize pictures of people playing cricket versus baseball in general? Maybe it just learned to recognize those 30. Maybe it's just cheating, right? That's what overfitting. We can go talking more about that during this course, right? But overfitting is where you don't learn to recognize pictures of, say, cricket versus baseball. It's just these particular cricketers, these particular photos, these particular baseball players, these particular photos. We have to make sure we don't. And so the way we do that is using something called a validation set. A validation set is a set of images that your model does not implement. And so these metrics, like in this case error rate, get printed out automatically using the validation set. A set of images that our model never got to see. When we created our data bunch, they automatically created a validation set for us. Okay? And we'll learn lots of ways of creating and using validation sets, but because we try to bake in all the best practices, we actually make it nearly impossible for you not to use a validation set. Because if you're not using a validation set, you don't know what to do. Okay? So we've always printed images on a validation set, we always hold it out, we always make sure the model doesn't touch it. That's all done for you. Okay? And that's all built into this data bunch object. So now we have one can just use a method called fit, but in practice, you should really always use a method called fit one cycle. We'll learn more about this during the course. But in short, one cycle learning is a paper that was released, I think, a few months ago, less than a year ago. So 2 months ago, and it turned out to be dramatically better, both more accurate and faster than any previous approach. So again, I don't want to teach you how to do 2017 deep learning. Right? In 2018, the best way to fit models is to do something called one cycle. We'll learn more about it, but for now, just know you should probably type fit one cycle. Right? If you forget how to type it, you can start typing a few letters in tab, okay, and you'll get a list of potential options.
Okay.
And then if you forget what to pass it, you can press Shift tab, and it'll show you exactly what to pass. So you don't actually have to type it. And again, this is kind of nice and couple of tabs here, because we can see cycle length, and we'll learn more about that. Is what it is in integer, and then that's value, right? Float or a function, whatever, and so forth. And you can see that momentum is going to default to this couple. Okay. So for now, just know that this number 4 basically decides how many times do we go through the entire data set, how many times do we show the data set to the model so that you can learn from it. Each time it sees a picture, it's going to get a little bit better, but it's going to take time. And if it sees the same picture too many times, it doesn't like that picture, but it's better. We'll learn all about how to tune this number during the next couple of lessons. But starting out with 4 is a pretty good start. You can see how it goes. And you can actually see after 4 epochs or 4 cycles, we've got an error rate of 6%. So,
Alright.
Our
results are pretty consistent.
Yeah. So we're paying 60 cents an hour. We just pay for 2 minutes at a time. We actually pay for the whole minutes on and running. So we use 2 minutes at a time. And we've got an error rate of 6%. So 94% of the time, we correctly pick the exact right mark of those 94 target categories. Which feels pretty good to me. But because of how it is, maybe we should go back and look at the paper. Just remember, I said the nice thing about using active papers or active data sets is we can compare our solution to whatever the best people can did or whatever the academics did. So this particular data set, the PET grades, is from 2012. And if I scroll through the paper, you'll generally find in any active paper there'll be a section called experiments about 2/3 of the way through. And if you find a section on experiments, then you can find a section on accuracy. And they've got lots of different models. And their models, as you'll read back in the paper, are extremely PET specific. They learn something about how PET heads look, how PET bodies look, and PET images in general. They combine them all together. And once they use all this complex code and math, they got an accuracy of 59%. Okay, so 2012, this highly PET specific analysis of accuracy of 59%, these were the top researchers from Oxford University. Then, in 2018, with basically, if you go back and look at actually how much code we just wrote, it's about 3 lines of code. The other stuff is just picking up to see what we're doing. We got 94%, so 6% error.
Wow.
So that gives you a sense of how far we've come with deep learning, particularly with PyTorch and FastAI, how easy things are. Yeah. So before we take a break, I just want to check to see if everyone. And just remember, if you're in the audience and you see a question that you want to ask, please click the one part next to it so that Rachel knows you want to hear about it. Also, if there is something with 6 bytes and Rachel didn't notice it, which is quite possible, just quote it and reply and say, hey, Rachel, this one's got 6 bytes. Okay, so what we're going to do is we're going to take a 8-minute break. So we'll come back at 8:05. So where we got to was we just trained a lot. We don't exactly know what that involved or how it happened, but we do know that with 3 or 4 lines of code, we built something which smashed the accuracy of 30 yards in 2012. 6% error certainly sounds like pretty impressive for something that we recognize as top grades and grades. But we don't really know why it works very well. That's okay, right? And in terms of getting the most out of this course, we very, very regularly hear after the course is finished the same basic feedback, which this is literally copy and pasted from the forum. I fell into the habit of watching lectures too much and Googling too much about concepts without running the code. At first I thought I'd just read it and then research the theory. And we keep hearing people saying, my number 1 regret is I just spent 17 hours doing that. And at the very end I started running the code and it turns out I learned a lot more. So please, run the code. Really run the code. I should have spent the majority of my time on actual code and notebook trying to see what goes in and seeing what comes out. So your most important skills to practice hard learning, and we're going to show you how to do this in a lot more detail, but understanding what goes in.
Alright, makes sense.
So we've already seen an example of looking at what goes in, which is data.showDash. And that's going to show you examples of labels and images. And so next, we're going to be seeing how to look at what came out. So that's the most important thing to say. As I said, the reason we've been able to do this so quickly is heavily because of the FastAI library. The FastAI library is pretty new, but it's already getting an extraordinary amount of traction. As you've seen, all of the major cloud providers have supported or are about to support it. A lot of researchers are starting to use it. It's really making a lot of things a lot easier, but it's also making new things possible. And so really understanding the FastAI software is something which is going to take you a long way. And the best way to really understand the FastAI software well is by using the FastAI documentation. And we'll be learning more about the FastAI documentation shortly. So how does it compare? I mean, there's really only one major other piece of software like FastAI, but it's something that tries to make deep learning easy to use. That's Keras. Keras is a really terrific piece of software. We actually used it for previous courses until we switched to FastAI. We ran the TensorFlow. It was kind of gold standard for making deep learning easy to use before, but life is much easier with FastAI. So if you look, for example, at last year's course exercise, which is getting close versus tens, FastAI lets you get much more accurate, less than half the error of completion set else. Training time is less than half the time. Lines of code is about 6 of the lines of code. Now, the lines of code are more important than you might realize, because the 31 lines of Keras code involve you making a lot of decisions, setting lots of parameters, doing lots of configuration. So that's all stuff where you have to know how to set those things to get the best practice results. Whereas these 5 lines of code, anytime we know what to do for you, we do it for you. Anytime we pick up a default, we do it for you. Okay? So hopefully you'll find this a really useful library. But it's a lot of learning, but taking a very long way. How far can you take it? Well, as you'll see, all the research we do with FastAI uses the library. And an example of the research we did, which was recently mentioned in Wired, describes a new breakthrough in natural language processing, which we call the ImageNet moment, which is basically we wrote a new state-of-the-art result in text classification, which OpenAI then built on top of our paper to do.
Alright, I don't know where he's going with this, but it seems to me like he's just talking a lot and not really showing us much. So, alright, so far we got to this point. We were able to run the model, and the model again is just this black box that we have no idea how it actually worked. This ResNet 34 model. And so we don't really care about that so far. Really, there's a lot of juggling with the data. Just make sure that it's in normalized form. It's follows a certain structure that this learner expects, and then once you got that, the rest of it is really just plugging the data into this pre-made model that's already been trained. So he's saying it's already been trained on ImageNet, this much larger data set. Okay, and then you hit fit one cycle, which is doing the actual learn. And you pass 4, that means 4 cycles, and that's enough to drop the error rate from 10%, our initial error rate, down to about 6.8%. And at that point, you just hit save, and you save stage 1. We haven't looked at the results yet, so we'll do that next. For now, though, the video is getting pretty long, so I'm going to go ahead and stop and continue in a bit. Ciao.